Hello, welcome again to another session of Operating System Concepts. Previously, we have looked at the mechanism that enables for processes to work together when they want resources from the system. But sometimes, problem does occur and the operating system must have a proper mechanism in order to overcome the problem. One of the most common problem in a multiprocessing system is the problem of deadlock. So what is actually deadlock? We will look at the problem of deadlock and also investigate the causes and basically the definition and also what can we do in order to prevent or perhaps avoid deadlock from happening. So in today's session, apart from the definition and getting to know about deadlock, we are going to look at the detection, prevention, and avoidance of deadlock. And at the end, we are going to understand how an integrated deadlock strategy can be designed from those detection, prevention, and avoidance. If you remember previously, we have looked at the problem of the dining philosophers. If you remember, we have 5 dining philosophers and each of them have to share the use of the forks in order to finish the spaghetti. Now, what happened if, let's say, one of the philosophers perhaps didn't want to actually give out the fork because it is actually waiting for another fork from another philosophers. So this is basically the background of something of a deadlock that is happening. So what is the definition of deadlock? By definition, deadlock happens when a set of processes is actually waiting or competing for a set of system resources and at the same time they are communicating. It means that, for example, we have process A, process B, and process C, and each of them are actually relying on the resources that is being held by each of the process. And what it meant by communicating is that process A actually requested from process B requested from process C, and process C requesting from process A. So each of them are actually in a set of system that is actually waiting for the resources that they want, but each of those resources is being held by the process. So, for example, process A, in order to finish the instruction, it requires the use of resources from process B and process C. While process B, in order to finish the process that it actually doing, it needs the resources from process A and process C. So, each of those processes cannot finish because the resources that it wants in order to finish the instruction is being held by another process. So this is where the problem lies, because you have processes that are waiting for another process to release the resources, but they cannot actually finish the instruction because each of those instructions requires the use of resources from another process. If you remember previously, we have many states of a process. Apart from it, we have the new, we have the ready, running, and also process that is being blocked. So what happens in a deadlock situation is that we have multiple processes that is being blocked. So in our previous example, A, because it cannot get the resources from B and C, it is being blocked. And then at the same time, B cannot get the resources from A and C, and also it's being blocked. And then also the same for C, it cannot finish because it is waiting for A and B, and hence it is also being blocked. So in this situation, we have A, B, and C that cannot actually execute because they are actually waiting for the resources that's being held by another process. And as a result, A, B, and C cannot execute, and then in this example, A, B, and C is inside the system and they cannot continue because the resources cannot be obtained. So how do we actually prevent or perhaps avoid deadlock from happening. If you remember previously, we have the mechanism of mutual exclusion. So one of the solution is, of course, we have a proper mutual exclusion mechanism in the system to ensure that no process is actually holding on to our resources if it's actually being blocked or cannot finish. So that is one of the mechanism to fix deadlock problem. But at the same time, modern operating system have other mechanisms such as perhaps to detect possible deadlock that could happen and perhaps try to avoid and perhaps try to actually overcome deadlock from happening. So this is where we are going to look at it in this chapter. So in the early days of the operating system, because deadlock is happening and none of the event that is waiting for the process A, B, and C previously didn't even occur. So when it happens, deadlock is actually permanent and there is no efficient solution in the general case during the early days of the operating system. Nowadays, if deadlock happens or perhaps your system hangs, you have the task manager to thank for that you can actually intervene and stop the hanging process. But in the old days, if deadlock happens, you cannot have other choices except you perhaps restart the system altogether. So that's why modern operating system have a mechanism to actually detect before deadlock can happen or perhaps try to avoid those conditions that could contribute to a deadlock from happening. So before we go further into identifying the condition that could contribute to the happening of a deadlock, we first look or take a step back and getting to know the different type of resources that is actually being needed by a process. Previously, in prior chapter, we have looked at some of the type of resources such as the I/O devices, we have memory, we have the processor. But basically, aside from the reusable resources such as those processors, I/O channels, and also secondary memory and main memory, we also have other type of resources such as the consumable. Consumable means usually means that sometimes we need some sort of user input, interrupt, signals that is needed by a process in order for it to continue. So the main resources that we have previously getting to know before are the reusable resources, and apart from those reusable resources, we also have consumable resources, which is something that can be created by another process or perhaps being consumed once a process actually ends. So before we go further, let's look at this problem of process Q and process P. So if you notice, both process Q and P are actually requesting the use of resources D and also resource T. So here in this example, we have two tables, both representing each of the process. Process P is on the left, process Q is on the right. So P0 until P6 actually represent the instruction for process P, while Q0 and also until Q6 represent the instruction actually being executed by process Q. So notice here, process P is requesting D and actually locking D, while on the other hand, process Q requesting T and locking T. So what happens next? Can you guess during process 2 instruction and also Q2 instruction? Can you guess it? Yes, you guessed it. During the instruction of process P2 is requesting for the use of resource T, while Q2 requesting the use of resource D. But if you notice earlier, the resource D is being locked by process P, while the resource T is being locked by process Q. So in this instance, both processes cannot actually continue because each of the needed resources is being held by another process. What is being needed by P is being held by Q, and also what is being needed by Q is being held by P. So this is an example of a deadlock situation. They cannot continue to the next instruction because the resources that they need in order to finish the instruction is being held by another process. Now, see this second example. So in this example, imagine there are just 200 kilobytes of memory available. So you have P1 and P2 actually requesting for the use of resources. Okay, take note, P1 for the first instruction requesting 80 kilobytes of memory. Okay, and then P2 requesting 70 kilobytes of memory. So how many memory have been used by both process? Okay, 80 plus 70, you have 150 kilobytes actually being used. Now imagine if the next instruction is being executed. So now P1 wants to request an additional 60 kilobytes. So you have 80 plus 70 plus 60 now. Alright, so you don't have enough memory to be given to either P1 or P2 because 80 plus 70 plus 60, we have more than 200 kilobytes of memory. So the memory is not available to be given to P1 and P2 because they have already been using the 150 earlier, and you have only a balance of 50 of available memory. Hence, you cannot give up 60 to P1 and you can also give up 80 to P2 because you don't have enough memory. So how do you actually draw a resource diagram to actually depict the use of resources by a process? So for example, in the above diagram in A, okay, let's say the circle is the resource and the square is the resource. So how do you actually read this diagram? So in this example in A, okay, P1, okay, the arrow is pointing towards the resource. So what do you read it is you have P1 is requesting the use of resource A. And then in B, you have resource that is being held. So here we have P1, okay, the arrow is pointing towards P1 from the resource. So how do you read it? P1 is actually holding resource A. Okay, so remember this diagram because perhaps you are going to use it later on when you're going to describe whether a process is actually requesting or a process is actually holding a resource. Just remember, if the process is actually pointing towards a resource, it just means that that process is requesting for the use of that resource. But if the arrow is pointing towards the process from a resource, it means that the process is actually holding the resource currently. Okay, so just remember again, if the process and the arrow is pointing towards a resource, it means that the process is requesting for the use of that resource. While on the other hand, if the process have the arrow pointing towards it from a resource, it means that the process is actually holding that resource. And then also, the node can be representing the amount of resources that is actually there. If you have one dot, it simply means that you have one resource. If you have two dots, you have more than one resources. Now, let us try to read the diagram C. So here we have P1 and the arrow is pointing towards resource A, and then resource A, the arrow is actually pointing towards process 2, and then process 2, the arrow is pointing towards resource B. So in this example, how do we read it? Is that P1 is requesting the use of resource A, and at the same time, resource A is being held by process P2, and then process P2 is actually requesting for the use of resource B, while resource B at the same time is being held by process 1. So diagram C is actually depicting a situation of a deadlock, because a resources that's being needed by another process is actually being held by another process. So C depicting a deadlock. Now let's take a look at diagram D. So in this diagram D, we have P1 at the same time, like previously, is pointing towards resource A. But if you notice, there are 3 dots of resource A, which depicts that there are more than one resource A available. And then RA, or resource A, actually one of it is being held by P2. And then P2 is requesting the use of resource B. And in this also situation, we have more than one resource B available. So diagram B depicts a non-deadlock situation, because we have more than one resource available and we have plenty of resource available to be given to P1 and also P2. So if you have enough resources to give to any needed process, hence deadlock will not happen. Now we look at this resource allocation graph. So you see P1, P2, P3, and P4. And also we have resource A, resource B, resource C, and resource D. So how do you actually describe this situation? How do you read this diagram? Can you read it? And does deadlock actually happen in this diagram? Do you see more than one resources? No, right? You only see only one resources for each A, B, C, and D. So how do you read it? So P1 is requesting the use of resource B, okay? And resource B is being held by process 2, and process 2 is really requesting for the use of resource C, but resource C is being held by process 3, and process 3 is really requesting the use of resource D, but resource D is being held by process 4, and process 4 is really requesting the use of resource A. So in this situation, we have a circle of requests between P1, P2, P3, and P4. So each of these contribute to the occurrence of a deadlock, because each of those processes is actually requesting the resources that they are not or cannot have because it's being held by another process. Okay, so we will look at the definition and examples of what could contribute the occurrence of a deadlock. So in this next part, we are going to look at what condition that actually contribute to the happening of deadlock. Okay, as always, take a 5-minute break before we continue to the next part. Okay, so before we continue, ask yourself, do you understand what is actually contributing to the occurrence of deadlock? And then how do you actually read the resource and also process diagram? Okay, if you have mastered those knowledge, feel free to continue to the next part. Now, there are 4 conditions to actually exist in a system for a deadlock to happen. So first of all, you must have a mutual exclusion condition. It means that only one process can actually use a resource at a time. That is the first condition. Secondly, there exists a hold and wait condition where a process may hold the allocated resources while awaiting assignment of others' resources. Third, there is no resources that can be possibly removed from a process, okay, that is actually holding it. So you have three conditions here. Now, if you have these three conditions, you still will not actually have a deadlock. Because why? You can still have mutual exclusion, you can still have hold and wait, you can still have a no preemption. It means that as long as a process is holding a resource, it cannot be forcibly removed. It also can have a hold and wait situation. But if it doesn't have the fourth condition, then deadlock will still not happen. So what is the fourth condition? The fourth condition simply means that you have a circular wait. What does circular wait means? It means that you can have mutual exclusion, you can have hold and wait, you can have a no preemption situation, but it will not actually contribute to a deadlock that would happen unless you have the fourth condition, which is actually a circular wait. It means that, let's say, in a cycle or in a circle of processes, you have process 1, process 2, and process 3. So let's say P1 in the example is actually requesting for the resources that's being used by P2, and at the same time we have P2 is actually requesting the resources that are being held by P3, and P3 is requesting for the use of resources that's being held by P1. So this is what it means by the circular wait. P1 waiting for P2, P2 waiting for P3, P3 waiting for P1. So if you don't have this process waiting for another resource from each other, then you will not have a deadlock. For example, P1 holding the resources, but the resource is not being needed by P2. And also P2 is also doing its own thing and doesn't bother for the resources being held by P1 and P3. So there is no processes waiting for each other. So when there is no waiting for resources that is being held by another process, so deadlock will not happen. So remember, you can have mutual exclusion, you can have hold and wait, you can have no preemption, but unless you have the fourth one, which is the circular wait, then deadlock will definitely happen. So these are the four conditions which contributes to the occurrence of a deadlock in a system. Now, once you know those four conditions, so how does it actually help you to deal with deadlock or when designing your own operating system in the future? Okay, you have those four conditions identified. So how is it actually beneficial for you to actually deal with a deadlock problem? So this is what this next section is all about. How do you actually deal with deadlock, knowing those four conditions that you can actually control and perhaps stop deadlock from happening. So in order to deal with deadlock, there are actually three general approaches to actually help to control deadlock from occurring in your system. There are prevention method, there are avoidance method, and also there are detection method. So prevent is actually adopting a policy in order to eliminate one of the four conditions which contribute to a deadlock happening. And then avoiding deadlock means that make appropriate dynamic choices based on the current state of the resources that is available. So you look at available resources and perhaps make calculated decision on which process can actually get the resource first. And then the third one is to actually detect deadlock before it actually happen and take action if actually deadlock happens. So you have prevention method, you have avoidance method, you have also detection method. So we look at those methods one by one in the next section. So in the first order is of course the prevention method. How do you actually prevent the four conditions from happening? Now, there are two approaches in actually preventing deadlock from happening. There are indirect approach and there are the direct approach. The indirect approach is actually to prevent the occurrence of the first three necessary conditions. Remember, you have mutual exclusion, we have no preemption, and we have the hold and wait condition. So you have to actually figure out a way to prevent those three conditions in order to use the indirect approach. And then the direct approach is actually to prevent the fourth condition, which is to disable the circular wait or to prevent the circular wait from happening. So first, we look at the indirect approach. So how do you actually prevent mutual exclusion and hold and wait first? Okay, so for preventing the mutual exclusion, so first of all, if actual access requires mutual exclusion, then those mutual exclusivity must be supported by the operating system. What does it mean? It means that if actually anything happen, the OS can actually intervene and perhaps stop the process that's being halted or perhaps release the resources that's being needed by another process. So this is what it means that OS must be in control of the situation if you provide mutual exclusion. Secondly, the occurrence of the hold and wait. Okay, so in this sense, a process must request all its required resources at one time. So let's say process A requires the use of resource A, resource B, and resource C. So from the very beginning, all process must declare how much resources and what resources are needed. Okay, you cannot just simply do one instruction, request a resource, do second instruction, request a resource, do the third instruction, request a resource. So the resource request must be done from the very beginning when a process is being declared. So by that, OS can actually estimate, okay, this process will need this much resource, the next process will need this much resource. So this is what it means that each process must declare what resources that it wants, so that the OS know beforehand or before its instruction is being executed how much resource is needed and when will it be needed. Now, for the third condition, no preemption. So in this case, if let's say a process is holding certain resources and is denied the further request from another resource, then it must release the currently held resources that is currently holding. So let's say for example, P1 is holding resource A, it is requesting resource B from P2. But currently, P2 is actually holding resource B, hence P1 cannot actually continue. So in this case, P1 must release resource A that is currently holding, regardless whether P2 is actually needed or not. So this is what it means that if you say you are requesting another resource but you cannot actually get it, then the current one that you're actually holding, you must actually release it. So this for the first indirect approach, you need to actually prevent the hold and wait, prevent the no preemption, and prevent the mutual exclusion. So if you actually have that, you must actually make sure that the OS is in control of each of those situations. So now we look at the direct approach. How do you actually prevent a circular wait? Now, in order to have a circular wait, you must have in your system or in your algorithm of operating system a linear ordering of resource types. What does it mean? So for this approach, we are actually going to use the Havender's linear ordering. So what does it actually do? So in this case, in your system, you must have a labeling or priority for resources. So you have higher priority resources and you have lower priority resources. Okay, so you label the resources accordingly, according to the criticality of the resources. So let's say in this case, or if you are using the linear ordering, so if a process is actually holding a higher resource ranking of value, it may not actually request a lower ranking resources. So the request order is done in accessing or accession value, meaning that you can request one process at a time from the lower ranking to the higher ranking, but you cannot actually request a higher ranking resource first and then you request a lower ranking resource. So in this case, usually the higher ranking resource is actually a much more critically needed resources. Okay, so you can actually request a rank up of resources, but you cannot actually request a rank down of the resources to prevent the uh, availability of higher ranking resources to be actually being used or fully utilized by the current process. So this is the direct approach of the prevention for deadlock. So now we are going to look at how to actually avoid deadlock from happening in a system. Now sometimes it's not also feasible to actually prevent the deadlock condition from happening because we always need mutual exclusion, we need the whole and weight, we need also the no preemption. So those three conditions still happens, but we make actually very controlled decision on how actually process being executed. So this is why previously, remember in avoidance, we try to actually estimate what is needed by each of the process, which is why from the very start of the process, each process must declare what resources is being needed for it to actually finish. Why? Because OS can make a very sound decision on which process can actually begin and which process must actually wait before it being granted execution. So in this case, the decision is made by the operating system dynamically, means that it will look at the needed resources being actually requested by the process before actually granted execution. So in this case, it requires the future process request knowledge because each of the process that wants to execute must declare how many resources that is needed for each instruction that it is going to execute. So by having that situation or having control of those knowledge, it can either have two conditions. Either you have resource allocation denial, where the process request will not be granted, or the second one is the process initiation denial, where a process cannot be started unless all the resources that's being needed by that process is actually available. So either you have one condition, resource allocation, or you can have one condition, the process initiation. This is the approach in the deadlock avoidance approach. So the resource allocation denial is also known as the banker's algorithm. Okay, just imagine if you're actually going to the bank. Okay, so you want to actually withdraw money. So you declare how much money do you need. Okay, and then the banker will actually check whether you actually have enough money to actually withdraw. So in this case, it will check all the available resources that you will need upon execution, and if you actually don't have enough resources to use, then you must actually wait until enough resources is there for you to use. There is a safe state and there is an unsafe state. Safe state means that there is at least one sequence of resource allocation that does not result in a deadlock, or there is an unsafe state, simply means that you don't have enough resources to actually being allocated for you to actually execute. So for that, we are going to continue in our next section. We are going to actually see how do you actually do this calculation of a safe and unsafe state. Alright, but for that, we will continue in our next session. So let's review what we have learned for today. First of all, there is the definition of deadlock. Okay, so remember what actually deadlock means. And remember, there are the resource allocation diagram. We have the process diagram, and also we have the resource diagram. And what does the arrow signify? Okay, try and practice again with the resource diagram and try to read the diagram and actually see the solution. And then secondly, the deadlock condition. We have the 4 conditions of deadlock. Try to understand those 4 conditions and try to actually relate how those 4 conditions is actually being used to controlling the deadlock. Okay. In the next section, we are going to actually see how to actually determine whether there is a safe state or an unsafe state based on the resource declaration that is actually being declared by the process and decided by the operating system. So until then, I hope you can actually master what we have covered in the first part, because we are actually going to use it later on in another chapter. So I thank you for joining to this session, and I hope it has been beneficial to you. Thank you very much.